Hello and welcome back to ML with Philip. In this video entitled RNNs tutorial generating names in different languages part 2, I am going to be digging deeper and we're going to continue where we left off in the first video when we learned how to create a recurrent neural network in order to generate names. This is a bonus video which contains extra information for those who are interested in digging deeper, but it's not absolutely necessary. If you haven't seen the first video, then go watch the first video before watching this video. I will link that video here for you to take a look at. In this video, I want to cover several things. The first thing is I want to add a start of sentence token to our names so that we can generate names without any prompt whatsoever. The next thing that I want to do is I want to replace our RNN with PyTorch's RNN class so that we can use their pre-built class and all of its functionality. The next thing that I want to do is I want to implement the ability to process the entire sequence at once instead of having to feed in each time step of the sequence. And finally, I also want to replace our RNN with a GRU and then later on with an LSTM. Now, I have done many of these similar things in a previous video, in the part 2 video to the classification problem where we had to classify the language that a name belonged to. But I want to do these again for this video because the character generation is quite different than just predicting a single language. You have to generate each character in each step of the sequence and then stop once your neural network has predicted the end of the sentence. So I think it is useful to do it again for this problem. So let's get started. All right, let's get to coding. The first thing that we want to do, as mentioned, is we're going to start by adding a start of sentence token to the beginning of our names. When we have a start of sentence token, that means that we can pass in the start of sentence token as our prompt, and it will generate a completely new name without even having to pass in the first letter. And this will be a fairly simple change, so let's go ahead and do that. We start with the same code as in the first video. What we need to do is in our name to tensor function, we are going to have to add in a start of sentence token at the beginning of the word. So instead of having the length of the name, we're actually going to have length of the name +1 because we're going to add a start of sentence token at the beginning of the word. Now, one thing that I want to make clear is that we can actually use the same end of sentence token at the start of a sentence and not have to have an extra special character, because when we use our end of sentence token, we're always trying to predict the end of sentence token. It never gets used as input. So if we place it at the start of sentence, then it now gets used as the input and it's not getting predicted. So we can actually just reuse that same token. So now what we need to do is at the 0th position, we're going to add the end of sentence token ID to the beginning of the name. And here we're just going to shift everything over by 1. And now here in the name to target function, we're actually going to take in the entire name because we're no longer using the first letter as the first input. So we can just remove this. Okay, now let's give that a try and see what we get. All right, so now let's take a look at the name tensor. So you can see that the name tensor now has the end of sentence token in the first position. And if we take a look at our target, it has the end of sentence token at the last position. So that all looks good. And now we can run through the steps of our neural network. And everything works. And we can even retrain our neural network. So I'm just going to let that run, and then we can check back in and we can try and generate some inputs without any prompt whatsoever. All right, our neural network has finished training and everything looks good. So now that it has learned to take in a start of sentence token, we can generate names with just the start of sentence token instead of giving it any characters. So let's take a look at our predict function because some things are going to have to change. In addition to the starting letters, we also are going to have one more token, which is going to be the start of sentence or end of sentence token. So we're not actually going to start at our starting letters first. We're going to start with the end of sentence token. Now, another thing that I wanted to show you guys that's going to have to change, if we take a look at our name2tensor function and we pass it just a single character, let's say B, it actually appends a start of sentence token to the beginning because it's treating this like a full name. So we're actually going to have to take in, instead of taking the name2tensor output at 0, which is what we have been doing because it only had one entry before, we're actually going to have to take the last entry because the first entry is always going to be the end of sentence token. So we're going to have to make that change here when we take in the input. So now we actually have the value of the letter B. Okay, so we're going to give it just an empty string, and we're going to take the, well, we can just keep it at -1, and we're going to take the input for the end of sentence token. And then we're going to pass that into our RNN as the initial input. So we have to do that step first. So pass through the start of sentence token as the first, and now we can take the starting letters and start passing those through the RNN to get our next character. And yeah, we set this to -1. So let's see here. Everything else should be mostly the same. This is always going to be -1. Okay, let's give that a try now. So we're going to give it no starting letters. We're going to give it an empty prompt. And okay, we have to take the language tensor and define it up here. Now let's give it a try. And we generated a completely new random last name called Lin. So let's do that for all of the languages now. Let's give it no prompt. Okay, these are some completely new last names that it was able to generate. Stock, Bryn, Abara, Kamata, Lin, Thun, Abakov, Baschal, Machalan, Rampon, Alvan, Patsen, Alberian, Marano, Mekchalan, Romen, Son, and Stovak. So some of these do sound like legitimate surnames, so I thought that was super cool. Okay, now the next thing that I want to do, now that we've been able to add a start of sentence token, is I want to replace our RNN that we built ourselves with Torch's RNN class. So this is going to be fairly straightforward. We're going to go into the RNN and we are going to replace our layers that we defined with Torch's RNN class. And it is going to take in, before we concatenated the input side, the input, the hidden, and the language. Now what we're going to do is we're going to treat the input with the language as the entire input, and we're going to treat the hidden as a separate vector. Our RNN is going to take in the input plus the language, and it's going to output the hidden size. And then we need an output to output layer in order to ensure that our output from the RNN is going to match up with our vocab length. And then in here, what we have is we're going to just concatenate the input and the language together. And we're going to leave the hidden as it is. And we're going to now go hidden comma output is equal to self.rnn of comma input. Sorry, the other way around. We're gonna have output comma hidden is equal to self.rnn of combined comma hidden. Okay, and then finally we're going to do output to output of the output. And we no longer need this. Okay, so this is what our RNN is going to look like. Let's give that a try. The first thing that we need to do before we do that though, is that the RNN class in PyTorch, it actually requires a additional dimension for the length of the sequence. So we're gonna have to fix that. So let's run everything. And now when we try to input it into our RNN, yeah, we can see that we got a 1D tensor, but it needs to be 2-dimensional. One thing that we can do is we can add an additional dimension here. And for our input, we can add an additional dimension here. Okay. So let's try that now. Our language tensor is also going to need an additional. So our language tensor is going to need an additional dimension here. And so we're going to do that. Okay, and here we're going to have to concatenate along the first dimension. So this is going to be dimension equals 1, and this is also going to be dimension equals 1. Let's try that now. Okay, it seems to be working. Okay, the output is also going to have an additional dimension. So we're just going to have to do this. And yeah, it looks like it's working now. So let's make those adjustments in our training script and see what we get. Okay, it seems like our neural network is training now. So let's give that some time and let it train, and let's take a look at the results once it's finished. Okay, our neural network has now finished training. Let's take a look at the results. Awesome, the results look significantly better than what we had before. So that's why it's advantageous to take advantage of some of the popular libraries which have implementations of neural network functions that have been implemented in a much more optimized way than what we have. Now, I'm not going to modify the prediction code to get it to work because we're actually going to make some additional changes, and we're going to have to go back and undo those later on if we do. All right, so now we have implemented the RNN class from PyTorch. What I want to do now is change our code so that we can take in the entire sequence at once instead of having to take in each time step by step. So let's do that now. So for this, we're actually going to undo some of the changes that we previously made. So we're now no longer going to have to take in a single input and index into that time step. We're just going to pass in the entire name tensor at once. So let's go ahead and do that. So this time we're going to get multiple outputs. And we're just going to pass in the entire name tensor. And we're going to get an error. So the error that we get here is that our language and our input don't match up. And that's because we have an input for every single time step, and we want to add on and concatenate the language information for each one of those time steps together. We're going to have to repeat our language vector for the number of times that we have in our time steps. So let's take a look at our language vector. It looks like this. It is just a single row. And if we take a look at our name tensor, there's multiple rows. So we actually want to repeat the language tensor the same number of times as we have rows in the name tensor. So we can use this repeat function, and we can have it go the number of rows that we have in our name tensor. And then we can add this extra dimension here. And there we go. We've now repeated the language tensor so that it has the same number of rows as the name tensor. And now we can concatenate it as expected. So let's add that code into our RNN class. And this is going to work whether we have a sequence with 5 characters or whether we have just a sequence with 1 character. It's still going to give us the same result. For example, if we had our name being just nothing, just the start of sentence token, and we used the language tensor that we had before, everything would work. And name underscore tensor dot size, and everything matches up. So that's what we needed to do. So let's get rid of this extra code now. We also have a multi-dimensional output, so we're going to need to have multiple targets as well. Let's go back and use a real name now. Okay, another thing is we have to also index into the target and the output that we want. To get the error for our prediction of the first character, we will want output at 0 and target at 0. And to get our error for the prediction of the first time step, this should be outputs at 0 and target at 0. And outputs at 1 and target at 1, and so on and so forth. So that's straightforward enough. Let's now adjust our training loop to make sure we account for that. We don't want to unsqueeze anything. We no longer need to go through this loop. So we can just get all of the outputs, and we can take in the entire input. And now we can go outputs at j, target at j, and now we can just calculate the loss for each output and each target. And I believe that's all we need to do here. So let's give that a try and see if it works. Wonderful. So it looks like our neural network is training as we expect, and we're no longer iterating through the time steps. We're just passing in the entire sequence. So let's check back in when it's finished training and take a look at the results. All right, so our neural network has finished training and the results look good. They look similar to what we had before, but now we get rid of that pesky for loop through the time. And we're going to have to make some adjustments to our predict function as well in order to make sure that it works. So let's go ahead and do that. Let's take a look at our name to tensor output. Name to tensor, we have everything here. So we can just pass all of that in, and we only need the final output because we're not going to be appending any characters on it. So we can just go input is equal to name to tensor of starting letters, and our output and our hidden is equal to this. But now we get multiple outputs. So we want to take the output at the last time step, and we do that. Output is equal to outputs at -1. And now our output is actually going to be two-dimensional. So let's just see what this produces. Okay, we want outputs at -1. But we also want to preserve the dimensionality, because remember our RNN requires 2 dimensions. So one thing we can actually do in order to preserve this dimensionality is we can index it like this. Sorry, like this. And that should give us the output that we want. So let's make all of those changes. And here we're going to want to do output at 0. We're going to do the same thing here. We only want the last letter and we don't want the start of sentence token. So that's going to be there. This is going to be here. Output at 0. And this. And it looks like it worked. So let's take a look at what our new neural network produces in terms of output. All right, our new neural network produces some pretty interesting last names. We've got Schrerer, Shelder, Saraf, Komoto, Sheng, Triu, Alerev, Pause, O'Hainer, Ardi, Arani, Kustos, Artono, Maro, Maki, Siren, Su, and Salowski. It seems like our network is getting even better. Now, the last thing that I want to do is I want to replace our RNN with a GRU and with an LSTM. So let's go ahead and do that. So I'm going to copy our RNN class. And I'm going to remove some of these comments just so that we can save some room. And everything is going to stay pretty much the same. Now all that we need to do is replace this RNN with our GRU class from PyTorch. And we can just rename all of this. And we should be good to go. All right, so it looks like our neural network is learning. So let's let that train and let's check back in and see what we get. All right, so our GRU has just finished training, and let's take a look at the results. And the results look even better than the RNN that we had. So that's great to see. The next thing that we're going to do is we're going to try and implement an LSTM as well. So that's going to be fairly straightforward. It's going to be similar to what we already did, but let's go ahead and go through that. Okay, so we're just going to copy our GRU class that we had from before. Now we're going to replace this with an LSTM. We're going to call this LSTM. And now our hidden state is actually going to consist of a hidden state and a cell state. So what we're going to do is we're actually going to have two of these. One for the hidden state and one for the cell state. And I think we're good just with those changes, but let's give it a try. Okay, seems to be working. Let's try and train this neural network and take a look at the results. Okay, seems to be training. Let's give it some time and then we'll check back in and take a look at what results we get. All right, guys, so we've trained our LSTM and we take a look at the results. And it doesn't seem to do as well as our GRU did, but it still was able to train and learn to solve the problem that we provided it with. That's what I wanted to cover in this video, and I just want to do a quick recap of everything that we've done in this video. So in this video, we did a few things. One, we simply added a start of sentence token at the beginning of our names so that we could generate names without any prompts. The next thing that we did is we redefined our neural network to use PyTorch's RNN class. After that, we modified our code so that we can input the entire sequence at once instead of iterating through the time steps. And then finally, what we did is we defined a GRU as well as an LSTM using PyTorch's classes. And with that, we were able to realize pretty significant improvements to our neural network, and we were also able to simplify some of our code. You've reached the end of the video. Thank you so much for watching, and I hope that you learned something new. If you enjoyed this video, then please leave a like, subscribe to my channel, and check out my other videos on my channel where I walk through and teach you how to build different machine learning applications. And check out the rest of the videos in this series, which I will link here at the end of the video. The next video is going to be super interesting, so I highly encourage you to take a look at that video where we solve a sequence-to-sequence problem and create a neural network using an encoder and decoder architecture with an attention mechanism in order to train a machine learning model to translate from the French language to the English language. This is a much more complex model and the results are pretty impressive. And we use everything that we learned in the first two videos because both our encoder and our decoder are built with RNNs. Take a look at that video. I think it's a very interesting one. And that's all from me. I'll see you in the next video.